So, question number 27. The wave function of the free particle of mass m constrained to move in a interval minus L to plus L. The wave function psi of x is equal to A is a normalization constant times L plus x times L minus x. A is a normalization constant. The probability of the particle will be found to have an energy. For this wave function, the particle represents the wave function psi of x. It is an even function. Should we have this energy? What is the probability? This is a question we are going to see that because we are going to solve it now.
Here the length of the infinite potential well is 2L. That means here the given interval minus L2 plus L. This is the length of the infinite potential well. That length A equal to 2L. The potential is infinity. The particle is inside the box. In general, the particle wave function they given us the psi of x equal to A into L plus x and then L minus x. Here if you look at the A is a normalization constant, L is the half length of the box, x is some variable. So if you multiply these two, it will give a plus b into a minus b, a square minus b square the form. That means the given function is an even function. If I interchange the minus sign for the variable x, it will give L square minus x square. That means I am changing the x variable sign. Because of the square, it will be again plus. So the wave function doesn't change. That means even if I am changing the variable minus x, we are getting back to the original wave function, the same form. So this is called the even function. So the given wave function is an even function, but they are asking the question, the probability that the particle will be found to have the energy. The particle will have the energy E equal to pi square h cut square divided by 2m L square. What is the energy of probability of finding the particle with this energy? So for that purpose, we need to write the energy of this infinite potential well. We already know what is this potential well energy. In general, the energy En equal to h cut square pi square n square divided by 2m. The length of the box square, that is a square, a equal to the 2L. That means the energy eigenvalue of this potential well n square h cut square pi square divided by 2m. If you are substituting a equal to 2L, it will be 2L whole square. So En equal to n square h cut square pi square divided by if I simplify this one, it will give 8m L square. This is the here it's n is a quantum number. N goes to 1 2 3 up to infinity. The 1 represents the ground state energy. So for the ground state energy inside the box, if you are finding E1 equal to 1 square, the first here it's n square, so 1 square, that means h square pi square 8m L square. So if you are doing the first excited state energy E2, that will be equal to, if you substitute the 2 here, 2 square means 4, so 4 h cut square pi square divided by 8m L square. If you are dividing this one, 4 are 4, 2 4 are 2, then 2 4 are 8, so it will give h square pi square 2m L square. So this is the first excited energy. Corresponding wave function for this energy, it's a psi 2. That means first excited state wave function. So their question is, what is the probability of finding the particle in this energy state for the given wave function? The given wave function is symmetric wave function. So the energy is the first excited state energy, because already we have done the energy E2 equal to h square pi square 2 ml square. E2 means it's first excited state. So the given energy is the first excited state energy, but the wave function is symmetric. Already we know the potential, infinite potential, the ground state wave function always symmetric. The first excited wave function should be anti-symmetric. So this is a ground state wave function, this is a psi 2. But the given wave function is a symmetric wave function. That means it should either represent the ground state energy. The symmetric wave function means it should represent the ground state energy. Only the first excited state wave function, it represents this energy. It's an anti-symmetric wave function. So the given energy is the first excited state energy. The wave function is symmetric. That means this wave function, that means the given particle never goes to the first excited state because it's a symmetric wave function. The first excited state wave function should be an anti-symmetric. So the with this energy, the probability of finding the particle in the first excited state, it would be 0. That means if you are finding the probability of the, if you are calculating the probability with this given wave function, it's a given wave function for the energy state, it will be goes to 0. That means even function never take any odd values of energy. That means first excited state, it won't be there. That is the meaning of that one.
So from our solution, the probability of finding the particle in the odd energy state with an even energy function will be 0, because there is no particle should have an even function should not have an odd energy state. The option is the first one, it's a 0.